Today's lesson comes from section 1.7 in our textbook, Introduction to Solving Inequalities. You can see our learning goals. We have discussed both of these in Algebra 1 previously, so it should be a good review and maybe just a good reminder about a few of our properties and rules about inequalities. Here is a little list. The properties will be very similar to the ones we used for our equations. That would be the addition property, the substitution property, subtraction, multiplication, division. All those properties are very similar. How you want to manipulate the equations to get the variables by themselves. Solutions, though, question is, how are they different? We need to start thinking. In an equation, we have one solution. In an inequality, there could be as many as infinite, all the way down to no solutions. So inequalities do change the solutions a bit. Compound inequalities, you should have learned, are basically where you have two inequalities separated by an and or nor. And the and situation, everything you want to think about, everything overlapping in both sets is what your solution should consist of. Some people call that the intersection of both sets. The or, all the solutions from at least one of the inequalities, or the union. If you think about the words and or, and let's put it in real life, if I would ask you to stand up because you're a winner today, if you have on a white shirt and blue pants. So if you have a white shirt and blue pants, stand right up. So everybody standing should have on both of those things. Whereas if I would have said, stand up because you're a winner today, if you have on a white shirt or blue pants. Now, anybody with a white shirt, regardless of what they have for pants, can stand up. Everybody who has on blue pants, regardless of what they have for a shirt, what color shirt they have on, can stand up. So we're talking about you only need one of the things if we're using the or. You need both of them if you're using the and. And that will be brought to light in a couple of our examples today. Now, before we move forward, I do want to review one couple things from inequalities that you should remember. If we just put up a true inequality here and start manipulating it using our four properties. Now, this is definitely a true statement, so nothing's wrong here, but if we took it and wanted to apply the addition property, let's say we wanted to add 2 to both sides. If we added 2, we'd now be looking at 5 is less than 7, a true statement. So if we use the addition property, nothing seems to be going wrong, going bad. However, 3 is less than 5. Let's do the subtraction property, and let's subtract 2, a negative. Let's just subtract 2 from both sides. And we would have 1 is less than 3. 1 is less than 3 is still a true statement. Now, if I would go back and say, well, does it matter if I subtracted a negative? And even if I subtract a negative, putting it up here in the original, coming down here, 3 plus a negative 2, in this case, would have been a 1. And 5 plus a negative 2 would have been a 3. We still ended up with a true statement. Doing subtraction. If I would have done subtract a negative 2 on both sides, 3 minus a negative 2 is 5. 5 minus a negative 2 is 7. 5 is less than 7. Still produces a true statement. So it did not matter whether we added a positive number to both sides or added a negative number to both sides. In both the adding and subtracting, we ended up with true statements both ways. Let's now go to the multiplication property. If we would multiply by 2, just keep it nice and easy for you, we get 6 is less than 10, which again is a true statement. If we immediately try to say, okay, let's multiply by a negative 2, we would get negative 6 is less than negative 10. Is negative 6 less than negative 10? Absolutely not. That is not a true statement. We would and should have learned that you take the negative 6, you switch the inequality sign to show that it is greater than your negative 10. You need to switch the inequality anytime you multiply by a negative number to make it a true statement. So now we have that true inequality. Negative 6 is greater than negative 10 because the greater the number is, the closer it is to 0. So closer it is to the right on the number line, lots of ways to think of it. So now we have a true statement. Let's do the same thing, but divide. So if we are dividing by 2 on both sides, we end up with 3 halves. If you don't like 3 halves, we could say 1.5 is less than 5 halves. Again, 2.5 if you like that better. 3 halves is less than 5 halves. 3 halves is 1 1/2, 2.5. We've got a true statement here. If we did the exact same division, but we divided by a negative 2 on both sides, we would have had a negative 3 halves is less than a negative 5 halves. Is negative 1.5 less than negative 2.5? And as most of you know, the answer is no. That would be a false statement. So to make this true, again, we will have to employ the rule that says you must switch the inequality sign anytime you multiply or divide by a negative number in order to result in that true statement. So be very careful. It's hard to remember as you're zipping along solving your equations, but anytime you multiply or divide by a negative number, not just because there's a negative in the inequality. So let's practice a few other types of inequalities and use those properties along the way. Here is just a basic inequality that has 2 variables and 2 unknowns. It's going to be solved very similar to our equations, and that was choose which side you want your variables on. Variables one way, numbers the other. I'm going to subtract 9 from both sides. When I do, that leaves us with 2y is less than 5y plus 6. I'll bring the 5y to the other side by subtracting. Now we will have a negative 3y is less than 6. We have a negative 3 here in our problem. We're going to have to undo that with a divide by negative 3. So here's a chance to use that property we just reviewed. If I divide by a negative 3, I must switch the inequality sign and reduce my fraction. So we'll end up with a solution of y is greater than negative 2. Again, label your number line with values that are close to where your solution is located. And now on your number line, you should graph only your solution. So we want all the values that are greater than a negative 2. So negative 2 does not make that true. So we need to start at negative 2 but not include it. We do that by doing an open circle. And then everything greater than would be to the right. And so our number line should show everything to the right. And then make sure we are going on to infinity by making that arrow larger than the original. So make sure your graph stands out and you can see your graph over the original line, either by using color or using, as I did, a squiggle to show the motion of the line. All right, let's try another one. This time, if you look, we have 2 inequalities separated by the word and. also known as a compound inequality. So we want to solve this and graph the solution. So statement one, you definitely want to take each inequality by itself, so sort of like standalone problems, solve them separately, and then look at your solutions and decide if it's an and statement, what type of solution are we really looking for? So in the beginning, let's subtract 3 from both sides of this left-hand inequality. 2x is greater than a negative 2. We'll divide by 2. When we divide by 2, x is greater than negative 1. Now you notice I did not switch the inequality on this one because I am not dividing by a negative 2. I'm dividing by a positive 2. So that is why the inequality did not change on this one. So right now we have solution x is greater than negative 1 to our first inequality. Go to our second. Looks like we need to get rid of a subtract 9 with an add 9. Leaves us 5x is less than 15. Undo the times by 5 with a divide by 5. That then leaves us x is less than 3. So we're looking for a solution where all the x values are less than 3. Do not forget to keep in consideration that and. That and tells you what has to happen with your inequalities. So right now, we want all the numbers that are greater than negative 1. So in your mind, you're thinking, okay, negative 1 and everything to the right. And then over here, but then I want all the x values that are less than 3. So you're thinking, okay, 3, and then everything less than would be to the left. Now, if you remember from our previous slide, and meant intersection. Everything in both solutions. So again, if we set up our number line on our solution to represent numbers around our solution, we should be looking at 3 and negative 1 are distinct beginning and ending points of this, and all the numbers in between. So if we were to graph, I believe we'd be looking at an open circle at negative 1, an open circle at 3, and then again, the line in between should be shaded. And there is our number line, because an and graph, one more time, is the intersection where both solutions cross, overlap, share values, and that is the only place. So the numbers on our number line represent values that would make both inequalities true. Another compound. This time it has the or in it. Solve 2b minus 3 is greater than 1, or 2b plus 7 is less than or equal to 1. Again, two separate inequalities, so solve each one separately, and then take into consideration the or. So, moving ahead that way, we'll add 3 to both sides. 2b is greater than or equal to 4. We'll divide by 2. b is greater than or equal to 2. Here's our solution for the left-hand side. Moving to the right, I believe we should subtract 6 from both sides. We'd have 3b is less than or equal to negative 5. Why did I subtract 6? Let's go back and clean that up. It looks like I should subtract a 7. Getting ahead of myself here. If we subtract 7, and that's why go back and subtract 7, we'd have 1 take away 7 is a negative 6. Now we're back on track. And divide by 3, divide by 3. Again, we are not going to switch the inequality sign because we're not dividing by a negative. We have a negative in the problem, but we're not dividing by it. And we look at a negative 2. So our inequality for the right-hand side, b is less than or equal to negative 2. Again, do not forget to bring down your word or that helps you put into perspective what your solution should be. Label number values around your solution on your number line, and only graph your final solution. So if you were graphing separately, you're thinking, okay, B is greater than 2. So I'm here, I'm at 2, and I'm everything to the right, you're thinking, and down here, B is less than or equal to negative 2, you're at negative 2, less than or equal. I now have colored in dots, and I should have colored in over here as well. 2 could be my solution. Less than or equal to, if it's less than, everything is to the left. This is an or. So B is greater than 2 and B is less than or equal to negative 2. Or was everything in both sets. So when we put these graphs on the number line, we need everything in both. So if we repeated and did a negative 2, closed circle because it's an equal to, and everything to the left, and then positive 2, closed circle because it's an equal to, and everything to the right, we would have a final graph that had pieces on both ends, a void in the middle, closed circles to represent the greater than or equal to, less than or equal to values. So you've seen several different types of graphs, styles of graph, based on the and or compound inequalities. And you should get familiar with graphing both types, compound inequalities, as well as the general inequality. So if you have questions about the graphs or any of these examples, bring them to class with you, and we will discuss them further as we practice problems in this section.